the answer to the problem where I talked about where the ball is thrown straight up into the air and comes back down, hits the ground. All right, so here's the basic sketch of what's going on. We have the ball being released. So I'm talking about from just after it leaves the hand, it reaches a peak, comes back down until just before it hits the ground. Because while the ball is touching the hand, and when the ball touches the ground, suddenly we have other forces involved and the problem becomes far more complicated. So let's just start out with a simple case where the ball is in the air only. We are ignoring air resistance as we do for almost all problems. Just to make simpler communication, at least for those with the math background, is that point A is the point at which the ball leaves the hand. So at point A, the ball is not touching the hand. Point B, the ball reaches the peak. C is when you get even with point A except on the way down. And D is just before hitting the ground. As always, as indicated on the other page, up is positive. Now, position. Position I established in the initial problem as position is 0 at the ground. And it even stated that over here. Position is 0 at the ground. So, while the ball is on the positive side of that, up was positive, while the ball's on the positive side of it, position is positive. And so, position is greater than 0 for the entire trip. And again, we can notate it also using this notation right here. I got brackets around the A and the D, and that indicates that from A to D, including A and D, and again, A is from when it leaves the hand all the way to point D, that is equal to, that is greater than 0. It's never equal to 0 because the ball doesn't touch the ground, and it's never less than 0 because the ball doesn't go below the ground. So that's position. So again, here's the problem as we go on to the next one. This is the notation that we're using here. All right, displacement. Again, displacement is positive when it's above, on the positive side of the starting point and below the starting, and on the negative side of the starting point. So displacement deals with change in position. So since we start at 0, we move up, we come back down. So as long as we're on the plus side of the starting point, then displacement is greater than 0. And so that is from A to C, not including. So using this notation over here, that I've got parentheses around it instead of the bracket. The parentheses indicate that A and C are not included. So from A to C, not including A and C, it's greater than 0. It's equal to 0 at A and C because I defined displacement to be 0 at point A. C is even with A. And then it's less than 0 below C until you get to D, including D. So I've got the parenthesis to indicate not including C, the bracket to indicate including D. And again, going back to the picture, it might be helpful if you write this down, but D is the point just before hitting the ground. Now, velocity. Velocity, positive or negative, depends upon the direction it's going. So if the ball is going up, it's positive. If it's going down, it's negative. Well, it's going up from A to B, not including B, and then going down after B. So we have velocity. It's greater than 0 from point A, including A, to B. Not at B, though. Again, I talked about this earlier, that if something goes from positive to negative, it has to go through 0, unless, of course, there's a rip in the space-time continuum. So at point B, that's the point where it flips direction. So for a brief moment, for a very brief moment, the ball stops. If it's going straight up, straight down. Now, I know in the drawing I had it going slightly off on the way down, but that's just for demonstration, just for drawing purposes. But at point B, the ball stops for just a brief moment and then starts coming back down. The velocity is less than 0 while it's going down, and that's from point B, not including B, to point D. And D was just before it hits the ground. Now, most students, if they've gotten into a conversation about this, have gone through this, and acceleration is where you get the biggest problems, because too many students associate acceleration with movement and not change in velocity, and that is key here. So if we think about it, at what point What is the direction of the force acting on the object while it's in the air? Because if you recall, motion has no memory. So once the ball leaves my hand, the motion of the ball doesn't care about how it got started. There was a physicist who, and I've heard it attributed to Einstein, I don't know if it's true or not, but made the comment that the future is more certain than the past. Because if I know where everything is in the direction that it's moving, then I have some good idea about what's going to happen next. But I have no idea about how it started in that motion. I walk along, I see a car going beside us. As the car goes beside, well, I know where it's going to be 1 second from now. But I don't know where it was, and if it's a straight road, say Utah, and there's nothing but straight road, I probably have a good idea of where that thing is 5 minutes from now. But 5 minutes ago, well, from a physics point of view, that car could have spontaneously just been produced, a second before I saw it. And so what's happened in the past really has no bearing on what's going to happen in the future in terms of motion. Now, so acceleration. The direction of the force acting on this thing is down. The thing starts out going fast, it slows down, stops for a moment, and comes back down. But the force acting on it is the force of gravity acting straight down. So the acceleration is down the entire time. So when is the acceleration positive? Not in this problem. 0? Nope. Not while it's, again, we're doing from the moment it leaves the hand to the moment right before it hits the ground, and it's less than 0 the entire trip. Now, some of you are thinking, but the acceleration at the top is 0. It's not moving. Again, going back to that misconception. Think about what would happen. Acceleration deals with the change in velocity over the change in time. If acceleration is 0, there's no change in velocity. Well, at the peak, the velocity is 0. So if acceleration and velocity are both 0 at the top, that means it's going to hover. Velocity is not changing, the velocity is 0, so that means it's not moving, so it's hovering right there, which is a really cool idea, but it just doesn't work that way. No matter how many times I've thrown things in the air, they have never stopped mid-flight and just hovered. Perhaps you've had a different experience. If you have, see if you can recreate it in front of other people. Videotape it without using any special effects. And then I might start to believe it. But until then, acceleration is negative the entire time. I hope you got them all right, and if not, I hope you learned about where the differences were and why your thinking might not have been accurate. Have a nice day.